I'm opening my files. I have to, Jupyter Notebook, I have to navigate to where my 310 folder is. And for me, it's quite a bit of navigation given how many files I have. So I'm just gonna actually start, this is the one we had last time. So right now, when I, for instance, so to continue your question about whether you have to restart again, I reopen this same file. It's sort of not executed. So in order to import NumPy, I can just go in here and execute Shift Enter or Shift Return, execute this cell, okay? And then it's gonna be re-imported, okay? So you kind of have to re-execute, even though it shows up as a list of cells, that doesn't mean that it has been, you have to run those cells in order for it to be imported again. Does that make sense? Because right now I just rebooted my computer and I opened everything up again. And it's not executed until I actually run it. I can run it from here, or I can click on an individual cell and run it, okay? So these are some little exercises that we did before. So this one has rerun, okay? And it kind of just blinks and executes the same thing. So now if I say x is np.log space 133 and print x, you have to print things, then I will get this 10, 100, and 1,000. Okay, so again, in logarithms of these three numbers are equally spaced when you use log space. And there's 3 values. I requested 3 values. Great. So now we will actually move on and introduce a couple of more functions. And then we will actually use some of these to start plotting things. Because in order to plot very smooth curves, I need a lot of points in between to plot them. And I'm not going to type that in manually. I don't want to, okay? So we're going to use these for plotting later on. So let's actually now just introduce a couple of more commonly used values. So one of them is random numbers. So often I want to just some sort of random numbers in between certain ranges, okay? And just there's these algorithms called random number generators, and one of them is actually already implemented in NumPy. And for that, I need an entire family of functions called np.random. And there's a function in there called rand. And then I give it sort of the dimensions of the array that I'd like generated. So let's just type in 4 and 2. That's going to be a 2-dimensional array. And I'm going to print R to see the result. So I got a 4x2 matrix as a result. Okay. And that 4x2 matrix has random numbers basically between 0 and 1. So by default, this function gives you random numbers between 0 and 1. Now, what if I actually wanted something else? So if I wanted porosities, okay, this would work. Theoretically, porosity is between 0 and 1. Okay. But in reality, I'm yet to see a sandstone that is 0.8 porosity, or 80%. Okay. That sandstone is collapsing if it exists, right? It cannot really support itself just by definition of that lithology. So most likely I'd like to scale this to some sort of porosity that is between 0 and 0.3, or even something like 0.10 and 0.3. Okay. So you can scale this, okay? And you can literally say, well, porosity is equal to, well, let's scale it. So 0.1 plus 0.2 times R. Okay. Now what does this do? This is my starting point, 0.1. And 0.2 is really difference, or the size of the range that I want to do. That's my 0.3 minus 0.1. And I'm actually going to type it in as 0.3 minus 0.1 times r. And I'm going to type in a comment. This scales r to 0.1, 0.3 range. Oh, and of course, I should print it to actually see what I've done. And now, indeed, I see that my values are between 0.1 and 0.3. So I can do that with any type of range I'd like. And I reiterate, the reason why we use NumPy is that it's going to operate on entire array. Okay? So I could have had, I'm going to redo this, I could have had 40 by 2. Okay? This is something larger. Or 4,000 by 2, or whatever. And when I do this, it still works on the entire array of 40 by 2. Okay, so it just takes the entire array and works with every value in this array. So these scaling that I'm doing here works with the entire array. That's actually often called vectorization. So I'm working with the entire vector, or in this case, actually matrix. Awesome, so I can do whatever I'd like to it. And then there is some constant values that I can generate.
Would you mind going back a little bit, because I didn't.
Okay. So any type of scaling, this could be any numbers you'd like to scale this data to. Now there's a couple of other functions that give me entire arrays. Typically matrices, but it could be anything. One is called ones, and another one is called zeros. If you kind of need to initialize something just to give it some space in the memory, you initialize it often with zeros. Okay? And then you replace those zeros with something more meaningful during your calculation. So that in that case, I would actually say R, or maybe I'm going to call it Z, is NP zeros. And you can do either 6, let's say 6 by 7. Whoa. Oh. Data type. I gave it an n-tuple and it doesn't like n-tuple. Remember n-tuples. And I need to print it. Okay. So I got myself 6 by 7 zeros. I could also just leave it as number, let's give it another one. O is NP0. So I can use this in multiple ways. I could just say 5 and then print O. And then you're just going to get 5 elements, one-dimensional. So if I just give it one number, it's going to give me one-dimensional array. If I give it a bracketed dimensions, 6 by 7, and this could, by the way, go on. It could be 6, 7, 3, and so forth. So I could have 3-dimensional array. That one's hard to look at, so I'm just not going to do it. But it does exist. Okay? And then similarly, you can do ones. So I'm just going to go with 1 or Z, O, okay, NP ones, and now I'm going to give it 7 values and print K.
Does that mean it's a 5 by 5 matrix?
No, it's 5 by 1. So if it's just 5, it's just 1 dimension. So if you give it 1 dimension, it gives you 1 dimension back. But that's a good point, because some other software might be implemented to give you a square matrix that is 5 by 5. You have to know that. You have to try it out and know. Yes, question?
How do you go about manipulating this data set that we created?
Anyway, so what do you want to do? Tell me.
Just insert some real values, I guess.
So you want to multiply it by 3.7?
Sure.
Okay, let's multiply K 3.7 times K. And here they are. Okay. Now, have I now a question for you. This 3.7 by k, it's printed for me. Okay? Is it saved in memory anywhere? No, it's just printed. So it just took the array, did the calculation and printed it for me. In order to have it in memory and work with it later, I have to save it into another variable. Does that make sense? So I can do that, which is what I did before.
Do L equals
Right.
3.7 times.
Look, I could have just say print and all of this. In which case, it's going to create this on the fly, print it for me, and be done with it. Okay? But I saved it in Z, so now Z is actually a variable I can work with. So if you need, sometimes you need to save stuff, sometimes you don't. You're the designer, you're the engineer. Okay? So it's just the options. So I'm not going to do that here, but here, if I wanted to save it, I would say, hey, A is, I'm so inventive with names, oh my. And then print A. And now A is something I can work with. Further do some other calculation and so forth. So, okay. But on the printout, result is the same. Right? If I just look at what I asked it to print. Okay. So those are the subtle differences, but they're important ones. Any other questions before I move on? So there are some other, you can also do identity matrix, which is sometimes helpful. I'm just going to add that one. Okay, so let me see that I didn't forget any of the function, and another one is diagonal. All right, so identity matrix of size 4, print I, just gives you that identity matrix as the last one in the list. 1, 1, 1, 1, 1 on diagonal, otherwise zeros. If I multiply any 4 by 4 matrix with this identity matrix, what happens?
They stay the same.
So nothing happens. It's like not multiplying the number 1. Okay? Just in the matrix world. All right. So let's now actually use this for some plotting. And for that, I'd like to actually open. So I can save this. Okay. And I'm going to actually open a new one. And I will go to File and say New Notebook. So again, feel free to explore all of these. I'm just using the essential stuff that is needed in a class, but you can actually make a copy, open, rename. So open would open something that you already have saved. You can download. Here is where you download as a notebook or a Python file. Okay. Also, you can download as a HTML. If you wanted to create a website and create some code that you want to present on your website, that would be the way. Okay. Everybody's like, what is a website? Why would I have one? I have a website. You can check it out.
Why doesn't it save it when you just click on it and save as, and it won't save it? Is that normal?
It should save as.
And then I
It's not
save
normal.
It, it says error saving file.
Right, so
Because IP
then you will come and address.
IP.
So I'm going to create a new one, and I'm going to call it Lecture 2.4 plots. And I'm going to say Spring. So I already uploaded a copy of it that has much more detailed notes that I don't have time to type in, but this is something that I'm writing as I go. And since this is a new notebook, I'm going to import myself NumPy. Basically, before you even wake up or anything, just open a file and type in import NumPy as NP. Okay? There's one more thing that I want to import, and that's going to be for plotting later. It's called matplotlib. And actually, I'm just going to do a specific subset of it that I need. So there is a family of functions in matplotlib, which is a pretty large collection. and that subfamily is called pyplot. And matplotlib.pyplot is too long to type, so I'm just going to call it PLT for short. Okay, so this as is I'm nicknaming it in order to reduce typing. Okay, so now what I want to do, I want to plot myself a sine function, very simple task. Okay, but for that I need to create some data and then compute sine of it and then plot it. I'm going to repeat. Create some point x, then compute sine x for it, and that's what I plot. So that's the key of plotting in any kind of software. You have to have or create points to plot. And by points, I mean full information on it. The fact that sine function exists as a function in NumPy means nothing for plotting until you actually create those plots one by one and tell it how to plot. And with plots, typically you create points and then you connect them somehow. Okay? So let's create first points, and I want to create function or plot function on 0 to 2 pi. That's how we typically plot the sine function in any kind of self-respecting trigonometry class. Okay? Because that's the entire period of sine function. So which function can I use to create myself 100 points between 0 and 2 pi? Log space? That's linspace. Log space I don't need for sine function. Okay? So it's NP linspace. Okay? And I'm going to tell linspace to start at 0. And then 2 times, luckily, pi, I could just put 3.14, but I don't have to. NP has it. And it's saved as a constant, np.pi. So I'm going to use that. And then I'm going to give it how many points? I'm going to say 100. I could also use a range, up to you. If you want to use a range, you can give it, it's the same format, just say a range here, and you would give it a spacing here, something like 0.05, okay? Up to you. So those are my points. And let me just double check. It's always good to double check as you go, especially when you're working with something new. And these are my points. Awesome. Okay, looks right. Okay. Okay, I don't need to print it. I'm gonna comment that, and I comment with my little hashtag. This is not Twitter, so it's not hashtag printx. It would be a very weird Twitter line. Okay, this is just a comment. And then I'm gonna compute sine of all of those. Okay. This being NumPy, things are vectorized. I can operate on the entire array. So actually, sine function that is in NumPy operates on this entire array. So all I need to do is say y is np.sine of x. And I can, again, print y just to check. Cool. And this is not, this is scientific notation, so this is 0.3, right? And it's value between 0 and 1. Awesome. Now, you can immediately see how this gets unwieldy pretty soon. This is why we need to plot. For any kind of human understanding of any set of points that is more than 10 of them, we need a plot, okay? Looking at a table with more than 10 values, humans are not good at it. Okay? So you need a graphical interpretation. Without that graphical interpretation, it's extremely hard to locate what's wrong in your data. Okay? So you have to plot. So we're going to turn off this printing because that ain't good. Again, by the way, there's research saying that humans are not very good.
How did you turn off the printing?
Hashtag. So just put hashtag and it's not going to print it. And now I'm going to use a default This PLT, this is this MATLAB.pyplot family of functions. They're simply a function plot. And the way a function plot works is you have to give it x values and y values. And those x and y values have to be arrays of matching points. So this one has 100 points and this one has 100 points. So when I go to the 0th value of x and 0th value of y, that defines me one point. Okay? Then the next one, the first value in the array, there's 0, I start with 0, then the first one. So x of 1, y of 1 is my second point. X of 2, y of 2 is my third point, and so forth. Yeah, you get my. Okay? So, and when I do plot like this, it's just going to plot those using some default settings. So let's see what those default settings are. Boom. Here we go. Does it look like a sign? Way better than just printout of those values. If I just gave you the printout of those values, you didn't know whether they were right or wrong, other than just looking at them all, if they're all between -1 and 1. Something's right about it, but it could be cosine for all you know, right? So this indeed is a sine function, and I can see that, so here there are 100 points, okay? Looks really smooth, but it's really plotting only those 100 points. Okay. Let me show it to you when it's not really smooth. So let's just change everything here and just say 10. Simple modification. This is the beauty of coding. I just change something up and execute again. And then it looks a little more choppy. Okay? Now you can actually see these 10 points. 1, 2, 3, 4, 5, and so forth. And in between those 10 points, it's just throwing in a straight line. Except that when that straight line is on a very small spacing, your eyes cannot figure out the difference. So that's that smoothness. It's actually fake smoothness. It's linear, piecewise linear. Okay? Piece by piece are just linear. Now your calculus question. Is this data, as shown here, differentiable? C1. Everywhere. What are the points where it's not differentiable? It's continuous, but it's not differentiable at these corners. Okay? So you gotta smooth it out to have that smoothly going. So it's piecewise linear function, and it's basically the derivative on every piece is a constant. But those constants have different slopes, so derivative of this would have one constant here, another constant here, but they would have mismatch. So you would get a discontinuity right there. And you're all like, why is she teaching calculus now? Okay. This is because sometimes you will want to do something to your data, but you have to understand that it's going to be understood by the computer as piecewise linear, and you might need to interpolate it differently to get it smooth. Yes?
So when it takes a tangent, it just does the slope between 2 points?
Yeah, that's all it does. It really just fits a line between 2 points. You know, if I now asked you to, hey, give me a line between these 2 points, you will know how to get it, right? So that's essentially all it does, and that's why the plotting is quick. And for visual representation, that works. For any further analysis, it might not. Okay. All right, so you can, again, let's go back to smooth. I'm just gonna re-execute 100. Okay, let's now do this a little more stuff. So if I asked you to give me just this, sure, here I can recognize as a sine function. I don't need to be Einstein to do that. But in any other cases, we have to label our plots. Okay, if you're going to present data to somebody, those plots should be labeled. So let's now add things to this that will label the plot. First thing I'm going to say, I'm going to label x-axis. And in this case, it's just going to be simple one, x. Oh, well. But it could be anything you need it to be. And I'm going to put a y label as sine of x. And when I re-execute, I can see that my x and y were labeled. So again, it's PLT X label and Y label. And if you had Z-axis, you could do Z label. I will also give it a title, though here this really tells me everything, but this is just to show you how it's done. Sine function. So if I do a title, title will be above the plot. I can also put it like this is just to kind of enable quick eyeballing where data is, especially when you have to look at something. You can just say, hey, let grid show. And this you just say, hey, let grid be true. This is a so-called Boolean or logical value that is either true or false. And you can toggle that on and off by saying false or true. Okay. So I'm just going to add grid. And I can also modify the axis to be precisely in certain range. Here it doesn't matter. It actually did a very good job of plotting pretty much within the range of my data, but sometimes I want to snap it onto a fixed grid. So here what I would do, I would say plot axis, and then go with 0 to 2 times NP, pi. So these are my x range from 0 to 2 pi, and my y range precisely from -1 to 1. So right now I can see that it's slightly, my axis goes a little above 1 and a little below -1. And here a little below 0 and a little above 2 pi. And that's what it does by default, and it's typically a good choice. But if you don't like that, you have a handle or a knob to turn, and then it's snapped on precisely into my grid. And my picky self, when I'm picky on Mondays, I like this. On Fridays, I couldn't care less whether there's an extra something on the plot. So I get less picky as I go through the week. All right, so now it's kind of perfectly aligned. Great. So basically, all of these are basically making your graph prettier. You didn't change data. You just manipulated how it's shown. Now let's say that I want to add more data. So I'm going to actually start with a new plot. And let's say I want to look at the difference between sine and cosine. You know everything about it, but I'm going to look at it anyway. So I'm going to create a new set of data. I'm going to call it y2, which is np cosine of x. So I want to now look at it together. I want to plot both. Okay? And why I want to distinguish the plots. So I can actually just say, hey, plt.plot of x, y. And let's see just what is it going to do. plt.plot x, y2. Oh, okay. It seems that by default it figured out, okay, I'm going to give it another color. Make it orange. But it's Python's choice of colors, not yours. And maybe you want to be a little more particular. If you want to be a little more particular, you can. Okay? So just remember from now on, you can modify everything that there is. I know how to modify a segment of things. A number of things I haven't even tried because whatever is a default works for me. So just embed that in your main, if you want, in your brain. If you want to modify, there is a way to find out how. Okay? And here we are just learning the basics. So we can actually, there's a set of modifications here that works on this one line that we plot. But if I want to plot two lines, then I would have to tell it which one to modify. And I might not, and in terms of axis, that's fine. This is all working on axis, so that's going to work on the entire plot. But if I wanted to kind of modify an individual line without asking for, hey, what is the address of this thing? Where do I go? Where do I go? On which door do I knock? I'm going to type it in immediately. And I'm going to say, hey, give me red circles. And I can do that. And I also want to label this. And label it as sine function. And the other one, I'm going to do blue crosses. And then label as cosine. And I can immediately actually execute this. Again, shift return or shift enter to execute. And I can see the difference. You can now see crosses, and you can see a little cross at every point we're plotting.
What does Vx mean?
X.
Vx.
B, blue, cross. So blue is the color. X is a
Instead of
type of,
just a single line, a smooth line.
it's just putting a dot of it. This is where it's actually useful to see only at 10 points. So I'm going to re-execute everything with 10 points. So this is 10 points. Let's re-execute with 10 points. Here we go. So now there are no lines anymore. I didn't tell it to put a line. I got into control, over control. I'm like, I like lines. Where are the lines? Well, actually, you can put a line. There we go. Now I told it to do a line too. It actually has a set of labels that it uses for colors, set of choices. So it's going to immediately, when you type in B, it's like, oh, that's one of the color choices. All right, I'm going to color in blue. And then when you type in X, oh, well, it knows it's not a color choice. It's actually a marker choice. So it's going to put it in. So it's smart like that. Okay? And you can actually mix up the order. Okay? Actually, I think so. I never did. Let's try. Let's do blue at the end. Yeah, you can mix up the order. So it immediately knows, hey. And then the third one is one of the line choices. Okay. And that line choice could be something else. It could be dashed. Ah, you have much more control than you know what to do with. So, I'm not going to go into many of details. These are some of the basic choices. What I want you to know is that, yes, you have a choice, and you can manipulate this to no end. Okay? And in your slides, there is actually a table with sets of choices you can play with. So if you like purple, go with purple by all means.
Yeah, I tried the P.
Huh? P is not a choice. So some of them are pre-programmed. So there's about a set of 7 or 8 pre-programmed colors. The rest, if you know what red, green, blue is in script, you can still go and define those. So you can define a color just by its red, green, and blue. So if you really want this Texas orange, you can program it. You find out what red, green, blue. So that can be your homework. By next time, figure out how to plot burnt orange. Okay? And let us know. Report back. All right. And then one more thing that I'd like to do is I'll actually plot a legend. Oh, that's a perfect ending. So if I say PLT legend, then these labels, okay, will show up here as any self-respecting engineering plot should have these if you have multiple things on your plot. Otherwise, your audience is struggling to figure out what it is that you're plotting. Okay? And actually, any self-respecting plot should have all of these, or at least this X. So I'm going to add that. And these labels are telling me that this is sine and cosine of X. Okay? All right, perfect ending for this class. We're going to continue on Wednesday.
Where are on Canvas the lectures? On which file?
I'm going to show you in a second. So on Canvas, there's folder with lectures, and there's also folder with code.
Yes.
This is saved as a lecture 2.4 something IPYNB, so all of it is in there with many more comments that I don't have time to type in. So you can load those into your notebook and execute.